So you saw a striking example of where friction helped us to balance. And now I want to discuss an object that is hanging and that can freely swing due to gravity. I want you to appreciate the situation of static equilibrium, that the sum of all forces and the sum of all torques have to be zero. So here's this object which I'm going to hang, maybe on the wall, and here is a point P, and there is a, let's say, a frictionless pin that I put in the wall, so the object can freely swing around. Let the center of mass be here, and so there is a force. If this object has a mass little m, there is a force mg, and here is the position vector r of P, and so it's clear that there is a torque relative to point P. And if there is a torque relative to point P, it would be Rp cross mg. I put a vector sign over here because you have to take the cross product between the two, so you take the sign of this angle has to be taken into account. This object is going to rotate. It's clearly going to rotate about that point P. The torque equals I about that point P times alpha, and alpha is the angular acceleration. How can we ever get a stable situation? Nature is now going to think hard and is going to say, gee, I can only have stable equilibrium if the sum of all forces equals zero, and if the sum of all torques relative to any point equals zero. And nature knows how to do that. That always will happen if P and the center of mass are along a vertical line. Because if that's the case, then there will be here a force mg, and then here there will be a force mg upwards. This object is hanging on that pin, so the pin action equals minus reaction will push upwards. So the sum of all forces is zero, and there is no torque. Take any point you want to, this point, or that point, or this point, or that point, or that point. There is no torque anymore. And so now there is complete equilibrium. So if you had an object, for instance, that looked like this, a thin rod, is a very massive object here, so that the center of mass is almost there, then this situation would be stable. Or you might say, this situation. Because now we have the center of mass and P vertical line. So also here we have now mg down. So we have at the pin mg up. Sum of all forces is zero. Sum of all torques is zero. But there is a big difference between this situation and this situation, which you immediately feel in your stomach, of course. And that is that this is highly unstable. If you just blow on this a little, it will swing over. It will start to rotate, whereas this is stable. If I move this to the side, it will come back to that position. But the basic idea is then that the center of mass will always, in stable configuration, line itself up below the point of suspension. I have here a triangle. And I have no clue where the center of mass is. It may be somewhere here. It may even be in open space. I don't know. What I can do now, I can suspend it like this. And I know that the center of mass must be below my finger. Did you notice? It's actually rotated. So that the center of mass lines itself up precisely below my finger. So I can now take a pencil and draw a line here. Or I can have a little string. And now I can change my finger to here. And I can again draw this line. And where the two intersect is the center of mass. So the center of mass will always find itself below the point of suspension. If now I take a piece of putty, and I put a piece of putty here, then clearly I changed the location of the center of mass quite substantially. It must have shifted enormously in this direction. Where is the center of mass? I have no clue. But look, I balance it here. The center of mass must now be somewhere here. I balance it here. Center of mass must be somewhere here. And where the two lines intersect could be in this opening. That's where the center of mass is located. So it's easy experimentally to find the center of mass. Earlier in the course, we calculated where the center of mass was. Perhaps you remember that when we had some very special geometrical configurations. I mentioned to you then already that there are ways that you can experimentally determine it, and that can be done very easily in the way I just showed you.